Welcome to Tungal Online Classes. In previous video, we have discussed some numerical problems on the basis of Newton's laws of cooling and the principle of a calorimeter. Right? So today we are going to discuss about gas laws. In that first one is Boyce law, Charles law, and third one is a Gay-Lussac law. So then, what are the statement of Boyce law? Right? Okay, see here the statement is at a constant temperature. The volume of a given mass of a gas is inversely proportional to the pressure, right? So this is the statement of Boyce law. At a constant temperature, the volume of a given mass of a gas is inversely proportional to the pressure. So in general, PV is equal to constant. Right? Or P1 V1 is equal to P2 V2, right? So this is the statement of Boyce law. What is the statement here? At a constant temperature, the volume of a given mass of a gas is inversely proportional to the pressure, right? If you draw the graph versus pressure versus 1 by volume, so in that case the graph is in straight line, right? If you draw the graph versus pressure versus 1 by volume, in that case the graph is in straight line. And the next one, if you draw the graph versus pressure versus volume, in that case the graph is like this. So this is about the Boyce law, right? At a constant temperature, the volume of a given mass of a gas is inversely proportional to the pressure, right? PV is equal to constant. In general, P1 V1 is equal to P2 V2. If you draw the graph versus pressure versus 1 by volume, then the graph is in straight line. And one more, if you draw the graph versus pressure versus volume, in that case the graph is like this, right? Okay. The next one is Charles law. So what is the statement of Charles law here? Pressure is equal to constant. At a constant pressure, the volume of a given mass of a gas is directly proportional to temperature, right? Charles law statement is at a constant pressure, the volume of a given mass of a gas is directly proportional to temperature. In general, that is V by T is equal to constant. Or V1 by T1, that is equal to V2 by T2, right? Okay. This is the second law, Charles law. At a constant pressure, the volume of a given mass of a gas is directly proportional to temperature. Then V by T is equal to constant. And the next one, Gay-Lussac law. Here, at a constant volume, the pressure of a given mass of a gas is directly proportional to temperature, right? At a constant volume, the pressure is directly proportional to temperature. So to remove this proportionality constant, we use the extra term, that is P by T is equal to constant. So this is about the gas laws. The first one, Boyce law, Charles law, Gay-Lussac law. The Boyce law statement, at a constant temperature, the volume of a given mass of a gas is inversely proportional to pressure. And Charles law is at a constant pressure, the volume of a given mass of a gas is directly proportional to temperature. Gay-Lussac law, at a constant volume, the pressure is directly proportional to temperature. So next one is ideal gas equation. It is very important for 3 marks. So then what do you mean by the ideal gas? So ideal gas means a gas which obey all the gas laws. So that is known as the ideal gas. Okay, see here. So from Boyce law, so this is the first answer. This is our equation number 1 and this is our equation number 2, right? Okay. The next one, we are going to derive the ideal gas equation. From Boyce law, V is inversely proportional to pressure. From Charles law, V is directly proportional to temperature. From these two equations, V is directly proportional to T by P. By cross multiplication, PV is directly proportional to temperature. To remove this proportionality constant, we use the extra term, that is R. R is the universal gas constant. R is the universal gas constant. For n mole of a gas, that is PV is equal to nRT. For n mole of a gas, PV is equal to nRT. Then next, from this one, R is the universal gas constant. R value is 8.314 joule per mole per Kelvin. Joule per mole per Kelvin. So this is the universal gas constant value. So that is 8.314 joule per mole per Kelvin, right? So this is very important for 3 marks. Next one, see here, show that alpha suffix V is equal to 1 by T. Show that alpha suffix V that is equal to 1 by T. Okay. So then what do you mean by this alpha suffix V? So alpha suffix V is the volume coefficient of a gas. Volume coefficient of a gas. Okay, see here. Here already we know that ideal gas equation. What is the ideal gas equation for n mole of a gas? That is PV is equal to nRT. PV is equal to nRT. Here we are differentiating this above equation. With respect to volume and temperature. Okay, differentiating this above equation with respect to volume is, that is P into dV, that is equal to nR. Here with respect to temperature, that is dt, right? So this is our equation number 1 and this is our equation number 2. Okay, so next one, we are dividing equation number 2 by equation number 1. Equation 2 by equation 1, right? Okay, what is the equation number 2 here? That is P dV, that is equal to nR dt. So divided by, here from equation number 1, that is PV, this is nRT. Here nR get cancelled, pressure get cancelled. So what are the remaining terms here? That is dV by V, that is equal to dt by T, Okay, the next one, take this term this side. So that is dV divided by V into dt, that is equal to 1 by T. So already we know that the expansion of a solid in expansion of a liquid in expansion of a gas, here the change in volume is directly proportional to initial volume and change in temperature, right? To remove this proportionality constant, we use the extra term, that is alpha suffix V into change in temperature, right? So from this relation, alpha suffix V is equal to change in volume by initial volume into change in temperature. Here del of E indicates that change in volume, del of T indicates that change in temperature. Here is also same, dV indicates that change in its volume, dt indicates that change in its temperature. So then we are replacing this whole term by this term. So that is alpha suffix V, that is equal to 1 by T, right? Alpha suffix V, that is equal to 1 by T. So it is very important for 3 marks. In last exam, they asked, show that alpha suffix V is equal to 1 by T for 3 marks. So what is the first step here? From ideal gas equation, PV is equal to nRT for n mole of a gas. Next, we are differentiating this equation with respect to volume and the temperature. Then equation becomes PdV is equal to nR dt. Then we are dividing equation number 2 by equation number 1. PdV divided by P into V is equal to nR dt divided by nRT. Here nR get cancelled, PP get cancelled. The remaining terms is, that is dV by V is equal to dt by T. So then by cross multiplication, dV divided by V into dt is equal to 1 by T. So this whole term becomes, that is alpha suffix V is equal to 1 by T. See the next topic here, black body. After that, we will discuss about the Stephen's law. So then what do you mean by the black body? Black body means a body which absorbs all the incident radiation of whatever of its wavelength. So that is known as the black body. So black body means a body which absorbs all the incident radiation of whatever of its wavelength. So that is known as the black body, right? So then the emissive power of a perfect black body. So emissive power, it is noted by small e letter. The emissive power of a perfect black body value is 1, right? Okay. The next one is a Stephen's law. The Stephen's law is very important, right? Okay, see here, the amount of heat energy radiated per second per unit area of a perfect black body is directly proportional to the fourth power of its absolute temperature. So this is the statement of Stephen's law. Okay, see here, the amount of heat energy radiated per second per unit area of a perfect black body is directly proportional to the fourth power of its absolute temperature, directly proportional to the fourth power of its absolute temperature. This is the statement of Stephen's law. Here capital E indicates that the amount of heat energy radiated, and T indicates that the time, A indicates that area, and small e indicates that emissive power, and capital T indicates that is absolute temperature. Right? Okay, then what is the statement here? The amount of heat energy radiated per second per unit area of a perfect black body is directly proportional to fourth power of its absolute temperature. The next one, to remove this proportionality constant, we use the extra term, that is E divided by T A E, that is equal to sigma. Sigma is the Stephen's constant. Sigma is the Stephen's constant into T to the power is 4. T to the power is, that is 4. Okay. The next one, from this relation, what is the expression to calculate the sigma here? Sigma is equal to energy radiated divided by time into area emissive power into T to the power is 4. So this expression we are used to calculate the sigma value. We are used to calculate the sigma value. Okay. The next one, from this relation, what is the expression to calculate the energy radiated? So that is E is equal to sigma area time emissive power into T to the power is 4. T to the power is 4. Okay. The next one. So from this one, what is the SI unit of sigma? SI unit of sigma. Okay, see here. So already we know that the SI unit of energy, the SI unit of energy is, that is joule. Next, SI unit of time is second, area is meter square, for emissive power there is no unit, and temperature is K to the power is 4. So then the SI unit is joule per second per meter square, K to the power is minus 4. K to the power is minus 4. This is the SI unit of sigma. And the next one, Cgs unit of sigma. Sigma is nothing but Stephen's constant. The Cgs unit of sigma is, in SI system energy is measured in terms of joule. In Cgs system, that is calorie per second per centimeter square, and C to the power is minus 4. Okay. See here, in SI system, the sigma unit is joule per second per meter square, K to the power is minus 4. So already we know that joules per second is nothing but watt. The joules per second is nothing but watt. So then the another unit to measure sigma is, that is watt per meter square, K to the power is minus 4. Right? Then what is the dimension formula for sigma? Dimension formula for sigma. Okay, see here. So already we know that the dimension formula for energy is, that is m L square, T to the power is minus 2. This is the dimension formula for energy, and the time is, that is capital T, and area is, that is L square. Right? There is no dimension formula for emissive power, and temperature is K to the power is 4. Then the dimension formula is, the dimension formula for sigma. Dimension formula for sigma, here this is m as it is, and here this is L square and this is L square. L to the power is 0, T to the power of minus 2, and this is T to the power is minus 3, and this is K to the power is minus 4. So this is the dimension formula for sigma. This is the dimension formula for sigma, right? This is about the Stephen's law. So here, what is the statement of the Stephen's law here? The amount of heat energy radiated per second per unit area of a perfect black body is directly proportional to the fourth power of its absolute temperature. Fourth power of its absolute temperature. Here, this is A by T into A into emissive power is directly proportional to T to the power is 4, and this expression we are used to find out the sigma. Right, the SI unit of this sigma is joules per second per meter square K to the power of minus 4, and this is Cgs unit, and this is the dimension formula. So then, what is the sigma value here? The sigma value is, that is 5.67 into 10 to the power of minus 8 joule per second per meter square K to the power is minus 4. So this is a standard value. So that sigma value, what is the sigma value here? That is 5.67 into 10 to the power of minus 8 joule per second per meter square K to the power is minus 4, right? Okay. See here, in case, consider this is a body, its temperature is T1, and another body is surrounded by the first body. Let us assume that this is A body and this is a B body. The A body is surrounded by the B body and its temperature is T2. This temperature is T2. So then, if T1 is greater than T2, this is a condition here. So here we are consider A body, its temperature is T1 and it is surrounded by the another body B, that is temperature is T2. Here the condition is T1 is greater than T2. T1 is greater than T2. Then here we are going to find out the energy emitted by the both the body. The energy emitted per second per unit area of a perfect black body. Right. Okay, see here. Then the energy emitted, so that is equal to energy emitted. So the first one is sigma area A1 time T T1 to the power is 4, right? This is E1 value and this is E2 value, that is sigma A2 T2 to the power is 4, right? Here we want to calculate the amount of heat energy radiated, So then E is equal to the amount of heat energy radiated, E is equal to E1 minus E2, that is sigma is common here, then A1 T T1 to the power is 4 minus A2 T2 to the power is 4. This is the expression we are used to find out the amount of heat energy radiated per second per unit area of a perfect black body. Okay, see here, the next one. Here, in case the area of the body is equal to 1 meter square and the time is 1 second, and for perfect black body emissive power is 1, right? Here the area of a body is 1 meter square, the time is 1 second, and emissive power of a perfect black body is, that is 1. So then the amount of heat energy radiated per second per unit area of a perfect black body, right? So substitute this all value in this equation, then E is equal to sigma, here area value is 1 and time is also 1, emissive power of a perfect black body is also 1, then it becomes T to the power is 4, right? So the amount of heat energy radiated per second per unit area of a perfect black body is directly proportional to T to the power is 4, then E is equal to sigma into T to the power is 4. So this is about the Stephen's law. See the problem here. The surface of the furnace is at 1700 degrees Celsius. Assuming that it is a perfect black body, how much heat energy radiated by 10 meters square of the surface in 1 hour, right? Okay. See here, in this problem they are given the surface of the furnace is at 1700 degrees Celsius, right? Right on the given terms here. The temperature is given, T is equal to 1700 degree Celsius. Assuming that it is a perfect black body, emissive power for a perfect black body is 1, E value is 1, right? So then how much heat energy radiated by 10 meters square? Area is also given. A is equal to 10 meters square of the surface in 1 hour. Time is also given, that is 1 hour, and the sigma value is given. Sigma value is 5.67 into 10 to the power of minus 8 watt per meter square. K to the power is minus 4, and here the energy E is equal to question mark. Energy is equal to question mark. Okay. See here, area is in SI system. Convert this into SI system, and this also in SI system. Then the temperature, that is T is equal to 1700 plus 273, that is equal to, so this is 1973, that is equal to 1.973 into 10 to the power 3 Kelvin. Right? Okay. Next, convert this time into second. So 1 hour means 60 minutes into 60 seconds, that is equal to 3600 seconds. Right? Already we know the formula. Energy is equal to sigma. Energy is equal to sigma into area into time into E. T to the power is 4. Substitute all the values here. E is equal to, what is sigma value here? That is 5.67 into 10 to the power is minus 8, and area is, that is 10 meters square. Area is 10 meters square, and the time, that is 3600 into emissive power is 1, and next temperature, that is 1.973 into 10 to the power is 3 to the power is 4. Right? Okay. Then E is equal to 5.67 into 10 to the power is minus 8 into, this is 3600 into 10 means 36300. Next, this is 1.973 into 10 to the power of 3 to the power is 4. So this is equal to 5.67 into 10 to the power is minus 8. So convert into decimal, 1, 2, 3, 4. 3.6 into 10 to the power is 4. 1, 2, 3, 4. And E is equal to this much. Multiply this one, we will get the final result is, that is 309.3099 into 10 to the power is, this is 10 to the power of minus 8, 10 to the power of 4, and this is 10 to the power of 3 to the power is 4 means that is 12. So then its result is 8. 309.3099 into 10 to the power of 8 joules. So this much of energy radiated from that surface. The next topic is mode of heat transformation. So already we know that heat is form of energy. It is always transferred from higher temperature region to the lower temperature region, or hot body to the cold body in different ways. Right? Okay. So in mode of heat transformation there are 3 types. One is a conduction. One is conduction. Second one is convection. And third one is a radiation. Right. Okay. So before we are discussing about this one, just see the general example here. So consider this is a classroom, and this classroom is consist of number of benches, right, and a person is standing at this position. Right? Here the so many students are there in the classroom. Let us assume these all are the students. Okay. So in this case, this person, he want to transfer this pen from first bench to last bench. So this is first bench and this is the last bench. In how many different ways he transfer this pen from first bench to last bench? The first possibility is, so let us assume that this is the first person, second person, third, fourth, fifth and sixth person, right? So the first possibility is, first person hand over this pen to second person, without moment, and second person is hand over this pen to third person hand over this pen to fourth person, so on. The finally this pen reaches to the last bench. So this is the first possibility. In first possibility, all the students are their respective place only, right? What is the first possibility here? The first person just is hand over this pen to second person hand over this pen to third person, so on. This pen that is reaches to the last bench. This is the first possibility. And the second possibility is, so this person, last bench person, is come and hand over this pen to first person, or first person is go and hand over this pen to last person, right? So in this case, this person is moving from first bench to last bench, and last person is moving from last bench to first bench. So this is the second possibility. And the third possibility, this person throw this pen to first person, or the first person is throw this pen to last person. In three different ways, this pen is transferring from first bench to last bench, right? In three different ways, the pen is transferred from first bench to last bench. Similar to this one. Here, what do you mean by conduction? Conduction, convention, radiation. So conduction means the heat is transferred from hot body to cold body, or hot end to cold end, without actual movement of the particles. Without actual movement of the particle. See here, this is the first possibility here. So in this case, the pen is transferred from first bench to second bench to third bench, so on. It reaches to the last bench. In that case, all the students are their respective place only. So that is the definition of a conduction. Here conduction means heat is transferred from hot body to cold body, or hot end to cold end, without actual movement of the particle. So that is known as the conduction. And the next one, convention means the heat is transferred from hot end to cold end with actual movement of the particle. So here there is a second possibility. So this person is go and hand over the pen to the last person, or last person come and hand over the pen to the first person. So here in convention, the heat is transferred from hot end to cold end with actual movement of the particle. And the last one, radiation. So radiation means the heat is transferred from hot end to cold end without interfering the intermediate medium, or without disturbing the intermediate medium. Here that is a third possibility. The first person throw this pen to last person, or the last person throw this pen to first person. So these are the definition of a conduction, convention, and the radiation. In conduction, heat is transferred from hot end to cold end without actual movement of the particle. In convention, heat is transferred from hot end to cold end with actual movement of the particle. And the radiation means heat is transferred from hot end to cold end, without interfering the intermediate medium. Okay. See here, in that first one, conduction. Okay. See here, in this case we are consider this is a rod. Can say this is a metal rod. The one end of this rod is rigidly fixed to the wall. The one end of this rod is rigidly fixed to the rod. The another end is free. So this rod is consist of n number of molecules. This rod is consist of n number of molecules. So in this case, we are going to supply some amount of heat energy to the another end. So in this case, consider this is the first molecule, second molecule, third, fourth, 5 and sixth molecule. So the first one, the first molecule, it absorbs the energy from the source. The first molecule, it absorbs the energy from the source. Once it gets sufficient energy, it starts vibrating about their equilibrium position. So for example, consider this a molecule. Once it gets sufficient energy, it starts vibrating about their mean position, right? So once it starts vibrating about their mean position, it starts disturbing the neighboring molecule. In that case, the energy is transferred from first molecule to the second molecule. The energy is transferred from first molecule to second molecule, and this second molecule also absorb the sufficient energy. It also starts vibrating about their mean position. In that case, this second molecule transfer the heat energy to the third molecule, and third molecule also gets sufficient energy. Again it starts vibrating about their equilibrium position and it disturbing the neighboring molecule. So on, this heat is transferred from hot end to the cold end, hot end to the cold end, without actual movement of the particle. So that is known as the conduction, right? The heat is transferred from hot end to cold end without actual movement of the particle. So that is known as the conduction, right? Okay, the next one, we are going to derive the expression for thermal conductivity. Expression for thermal conductivity. Expression for thermal conductivity. So in this case, consider this is a cube. So consider this is a cube. So this cube is consist of 6 phase. This cube is consist of 6 phase. So this is first phase, second phase, third phase, fourth phase, fifth phase, and sixth phase. So in this case, we are consider the 2 phase. This is A, B, C, D. So this is our first phase of the cube. And the second phase is E, F, G, H. So this is the second phase. This is the second phase of the cube. And the distance between these two phases, so that is known as the D. The distance between these two phases, that is known as the D. And here the temperature of this first phase is T1 and the temperature of the second phase is T2. Here the condition is T1 is greater than T2. Here the condition is T1 is greater than T2. If T1 is greater than T2 means the temperature of the first phase is more comparing to the temperature of the second phase. The temperature of the first phase is more than the temperature of the second phase. So then here the temperature is more means, so this is the hot end and this is the cold end. Then the heat is transferred from hot end to cold end. So that means the heat is transferred from first phase to second phase. See here, the quantity of heat energy it is transferring from first phase to second phase is directly proportional to the area of the phases. It is directly proportional to the area of the phases. And the quantity of heat energy it is transferring from first phase to second phase, that is Q is directly proportional to time. Q is directly proportional to time. And the next one, Q is directly proportional to change in temperature. Q is directly proportional to change in temperature. And the Q is inversely proportional to the distance between the two phases. The Q is inversely proportional to the distance between the two phases. Okay. So from all this equation, Q is directly proportional to area, time, change in temperature divided by D. Q is directly proportional to area, time, change in temperature divided by D. To remove this proportionality constant, we use the extra term, that is K. Q is equal to K area into T change in temperature divided by D. Change in temperature divided by D. Here K indicates that, that is the coefficient of a thermal conductivity. K indicates that is the coefficient of a thermal conductivity. So from this relation, K is equal to Q into D divided by area into time into change in temperature. Area into time into change in temperature. Okay. So then what is the SI unit of this K value? Right. So this expression we are used to find out the coefficient of a thermal conductivity. Then what is the SI unit of this coefficient of a thermal conductivity? So SI unit is, here already we know that energy is joule, distance is meter, and here area is meter square, time is second, change in temperature is Kelvin. Here 1 meter get cancelled. Then SI unit of K is, that is joule per second per meter per Kelvin. So this is the SI unit of K. So that is joule per second per meter per Kelvin or watt per meter per Kelvin. So this is the SI unit. And the Cgs unit of K. Cgs unit of K. So that is calorie per second per centimeter per degree Celsius, per degree Celsius. So this is the Cgs unit. So this is the SI unit and this is Cgs unit. And the next one is the dimension formula. Dimension formula for coefficient of thermal conductivity. So already we know that the dimension formula for energy, that is m L square T to the power is minus 2, and here the dimension formula for distance is L, dimension formula for area is L square, and dimension formula for time is T, dimension formula for change in temperature is K. Then here this L square and this L square, then dimension formula becomes m as it is, m L square both are get cancelled, the remaining is L, m L T to the power is minus 3, T to the power is minus 3, K to the power is minus 1. So this is the dimension formula. This is a dimension formula for coefficient of a thermal conductivity. Okay. So then let us assume that if a distance is equal to 1 meter, if the distance is equal to 1 meter, d is equal to 1 meter, area is 1 meter square, then the change in temperature or the temperature difference between these two phases is, that is 1 Kelvin or 1 degree Celsius, and the time t is equal to 1 second. So in that case K is equal to Q, right? If we substitute d is equal to 1 meter, area is equal to 1 meter square, and change in temperature equal to 1 degree Kelvin, and t is equal to 1 second, so then K is equal to, that is the Q, right? So in this case this formula is very important to calculate the amount of heat transfer from hot end to cold end, that is Q is equal to K into area into time into change in temperature divided by distance, that is d, right? And this expression we are used to find out the coefficient of thermal conductivity. So this is about the mode of heat transformation, So here we have discussed the heat is transferred from hot body to cold body or hot end to cold end in 3 different ways. The first one is the conduction, convection, and the radiation. In conduction, the heat is transferred from hot end to cold end without actual movement of the particle. So that is the definition of a conduction. So in examination they may ask for 1 mark, what is the definition of a conduction? The heat is transferred from hot end to cold end without actual movement of the particle. So that is known as a conduction. Convection means the heat is transferred from hot end to cold end with actual movement of the particle. And the last one is the radiation. Heat is transferred from hot end to cold end without affecting the intermediate medium. And this is the derivation of the expression for thermal conductivity, right? So here in this case we are consider a cube, and this cube is consist of 6 faces. In that case we are consider 2 phase. This is the first phase and this is the second phase. The temperature of first phase is T1, area of this phase is A, and the temperature of a second phase is T2, area of this one is also same, that is A, and the distance between these two is D. Here the condition is T1 is greater than T2, here the condition is T1 is greater than T2. So then T1 is greater than T2 means this is a hot end, this is a cold end. Heat is transferred from hot end to cold end. It is directly proportional to area, directly proportional to time, directly proportional to temperature difference, and inversely proportional to D. From all this equation, Q is equal to K into A into T, change in temperature divided by D. Here K indicates that is a coefficient of thermal conductivity, and this expression we are used to find out the coefficient of thermal conductivity, and this SI unit, Cgs unit, and this is the dimension formula. Okay, see here the convention, general example for convention is, so consider this is a beaker, that beaker is a consist of some amount of water, right? So here the initial temperature of this water is, assume that is 30 degrees Celsius, right? So here we are going to supply some amount of heat energy to this beaker. In that case, the first one, the base of this beaker absorb the energy. So afterwards this liquid absorb the energy from the base of this beaker, right? So once it absorb the energy, it starts expanding. Means the distance between the molecule is increased, right? Here the distance between the molecule is increased, right? So So if the distance between these two molecules is increased, means the volume of this liquid is increased. If the volume of the liquid is increased, so already we know that the density is equal to mass per unit volume. Mass per unit volume. So when this liquid absorbs the energy from the base of this beaker, in that case the volume of this liquid is increased. If the volume of this liquid is increased, this means the density of this liquid is decreased. The density of this liquid is decreased. So here the density of a cold water, is more comparing to the density of a hot water, right? So here this lower liquid molecule absorb the energy from the base of this beaker and its volume is increased. If its volume is increased, means the density is decreased. If the density is decreased, means so this layer of liquid, it is move in upward direction, and this is a cold water. The density of this cold water is more comparing to the density of this hot water. So this liquid, it is move in downward direction, or this liquid, it is overlap to this region. So in this case, the heat is transferred from hot end to cold end with actual movement of the particle. So in this case, these particles are moving in upper region, and these particles are moving lower region. So this is the definition of convection. So heat is transferred from hot end to cold end with actual movement of the particle, right? See the problem here. One face of a copper plate of area 5 meters square and thickness 0.01 meter is in contact with the boiling water at 100 degrees Celsius. The other face is at 0 degrees Celsius. In a steady state, the heat is conducted in 1 second, right? So write down the given terms here. The area is given, A is equal to 5 meters square. Thickness is D is equal to, thickness is nothing but the distance between the two faces, that is 0.01 meter, and the temperature is given, T1 is equal to 100 degrees Celsius and T2 is equal to, that is 0 degrees Celsius. In a steady state, find the heat conducted, that means Q is equal to question mark, and time is given, T is equal to 1 second, and K is equal to coefficient of thermal conductivity 400 watt per meter per Kelvin, watt per meter per Kelvin. So already we know the formula to calculate the amount of heat is transferred, that is Q is equal to A, K, T, temperature difference divided by distance, right? Okay. Here Q is equal to, K value is given, that is 400 into area is 5 meters square, time is 1 second, temperature difference is T2 minus T1, T1 minus T2, T1 value is 100, T2 value is 0, that is 100 minus 0 divided by the distance or thickness 0.01. Okay, then Q is equal to 4 into 10 to the power is 2 into 5 into 100 means, that is 10 to the power is 2 divided by 0.01 means 10 to the power is minus 2. So then Q is equal to 5 into 4, that is 20 into 10 to the power is 2, that is 6 joules. This much amount of heat is radiated or conducted, that is Q is equal to 20 into 10 to the power of 6 joules. The thermal properties of matter chapter is completed, and this is one homework, so that is write a short note on a greenhouse effect. Thank you.